So we're going to talk about the different kinds of reactions. One is a precipitation reaction, and this is a reaction that forms a solid. You take two aqueous solutions and you mix them together, and a solid forms. The example we had earlier was, wrong way. Sodium carbonate in laundry detergent reacts with magnesium and calcium ions and forms solids. And they precipitate out of solution. They fall out of solution. Here's an example. Here is lead iodide, which is a soluble ionic compound, and potassium iodide and lead nitrate. So here, both of those solutions are colorless and clear. Here's the potassium iodide. Here's the lead nitrate solution. When we mix them together, we get a yellow solid forming. It's like a cloud. And the reason it's cloudy is because it's little particles of lead iodide that are being formed there. So that's an example of a precipitation reaction. You don't get a precipitation every time you mix two aqueous solutions. If we mix potassium iodide and sodium chloride, it looks like we're doing exactly the same thing, but nothing seems to happen. Because when we mix these, the sodium, potassium, iodide, and chloride ions just all stay in solution, and they don't form an insoluble ionic compound. You only get a precipitation reaction if you form an insoluble compound. And so what we're going to learn how to do is predict the possible products and then go back and use the table of solubilities to identify if they're soluble or insoluble. So let's look in depth at what happens when potassium iodide and lead nitrate are mixed. So here's a beaker with the potassium iodide. When an ionic solid dissolves in water, the ions separate. And in my crazy analogy, this is two people going to a party. They separate and they mingle. And over here, we've got lead ions and nitrate ions. The nitrate ions dissolve as an intact unit, but they're separate from the lead, and they're mixing around. Immediately after mixing, we have all of these ions together in one beaker. But now we have the potential for lead to interact with iodide and potassium to interact with nitrate. That wasn't possible before. See, because the lead and the iodide were separated from each other. So what are our possible combinations? Well, we've got potassium ions and lead ions, and we've got nitrate ions, and we've got iodide ions. Well, this combination, I'm making a table here, it's not real obvious. This combination between potassium and iodide, that's not going to make a solid, right? Because that's one of the reactants. It was soluble. And this isn't going to make a solid, the lead and the nitrate, because that was one of the reactants. It dissolved in the water. So that yellow solid must be either potassium with nitrate or lead with iodide. And if we look it up in the solubility table, we find out that it is the lead iodide. Iodide compounds are generally soluble except when lead's around. Lead and iodide just really hit it off. They stick together. They go off and they make a solid, and they're not going to mingle around. The potassium ions and the nitrate ions just stay floating around in solution. Any questions? So we need to learn how to write equations for precipitation reactions. We'll go through all these steps and then we'll do some examples. We write the formulas of the two compounds as the reactants in a chemical equation, and then below that we're going to write the formulas of the ions. Be sure to include the charges. Sometimes we reverse these steps. If they give us a name instead of a formula, we'll write the ions and then the formula. Then we're going to swap partners, exchange ions. and rewrite those formulas on the product side, and then we're going to use the solubility rules to see if either of those compounds is insoluble. If both are soluble, then no reaction occurred. And you just write no reaction, or you can even abbreviate it NR, no reaction. If one or both of the products is insoluble, then you need to write the formulas, indicate the states, and then you have to balance the equation. When you're balancing the equation, do not change the formulas. You can't do that. Let's do an example. Write an equation for the precipitation reaction that occurs, if any, when solutions of potassium hydroxide and nickel 2 bromide are mixed. So here they're just giving us the names of the reactants. So this is a little practice from nomenclature from chapter 5. Potassium hydroxide. 2 words, 2 ions. The first ion is potassium, the second is hydroxide. So because I'm given the name, I'm going to write the ion formulas first. Potassium is K+, hydroxide is OH-. If you're still iffy on the chapter 5 stuff, get some help with that, okay? Until you get that straightened out, this stuff's going to be really, really hard. And I can help you, but I can't read your mind. I don't know exactly what thing you're struggling with, so you have to actually talk to me or find somebody else who can help you. So we look at those K+ and OH-, the charges are the same, so the formula for the compound is just KOH. We know that the state of this is aqueous because we're told that it's a solution of potassium hydroxide. So there's one reactant. The other reactant is nickel 2 bromide. So I'm going to put my formula for my reactant here. I'm going to write, though, the ions below it. Ni 2+, nickel 2, and bromide is Br-. So when I put those together, I'm going to get NiBr2. That's also aqueous because I was told that it was a solution. Any questions yet? So those are the reactants. We've got, you could imagine one beaker with potassium hydroxide solution, one beaker with nickel bromide solution. And then we're going to pour them together and see what happens. So what we're going to do is we're going to swap partners. Again, important to keep positive, negative. This positive ion is going to be attracted to this negative ion. This positive with that negative. We're never going to have an ionic compound formed between 2 ions with the same charge because like charges repel each other. So I'm switching partners, and I'm just going to write them with their new partners over here on the product side. So now K is going to be with Br, and the nickel is going to be with hydroxide. You need the charges so that you can write the correct formulas. Now, occasionally it'll save you a little time if you check out their solubilities first. So if we go to the table and we look up potassium compounds, we see that compounds containing potassium are generally soluble and there are no exceptions. So this one we know is aqueous. If we go look, compound formed between nickel and hydroxide, hydroxide is in the lower part of that table. Hydroxide compounds are generally insoluble, with a few exceptions. This is not an exception. So this one is insoluble, so its state is a solid. One of our products is solid, and so we do have a reaction and we need to finish. K+ and Br-, the charges are the same but opposite in sign, so we just need one of each. K, Br, and then I'm going to put aqueous in parentheses. And then over here I've got nickel 2+ and hydroxide minus. So I need 2 hydroxides to balance the charge on the nickel. So this is going to be NiOH2, and I ran out of space. And that has the state symbol S, because that's our precipitate. Then we need to balance the equation. Notice that what happened here is these ions just switched partners. The hydroxide ion is still intact. It didn't come apart. So we can balance that as a unit. That usually makes things a lot faster. So you can look at, okay, I've got 1 OH over here. I've got 2 OHs over there. So that tells me I need to put a 2 in front of KOH. That would give me 2 OHs here, and I've got 2 over there. And then I've got 2 potassium ions, but I only have 1 over here. So I want to put a 2 in front of KBr. Now I've got 2 potassiums on each side. There's nickel, there's 1 nickel there, and 1 nickel on this side. So that's balanced. Here I've got 2 bromines, and here I've got 2 bromines. And so now I have my balanced chemical equation. Any questions? Let's do another one. Mixing ammonium chloride solution and iron 3 nitrate solution. So again, we need the ions, and then we're going to make the formulas. So ammonium is NH4 plus, chloride is Cl minus. So that will go together as NH4Cl. But that's aqueous, because we're told it's a solution. You could also look it up in the table. Iron 3 is Fe3 plus. Remember, the Roman numeral gives us the charge, not how many, the charge. So it's Fe3 plus. Nitrate, you're supposed to memorize, is NO3 minus. When we put those together, we need 3 nitrates to balance the charge on the iron. And I'm really going to run out of room this time. So we have our reactants, and now we're going to swap ions, swap partners, and we could end up with iron and chloride, and we could get ammonium and nitrate. We need to look these up and see, are they soluble in water? Well, if we look up combination of iron 3 and chloride, we see that chloride compounds are generally soluble. There's a couple of exceptions listed, but iron is not one of them. So iron 3 chloride is soluble. This is aqueous. Ammonium and nitrate. Ammonium compounds are soluble, no exceptions. Nitrate compounds are soluble, no exceptions. Is there a precipitate that forms? No, there's no precipitate. That means there's no chemical reaction. All we did was mix some ions. That's not a chemical change. NR. No reaction. Any questions? There's another one. Potassium sulfate and strontium nitrate. What's the formula for potassium ion? K plus. And what's sulfate? SO4, 2 minus. So when we put those together, we get K2SO4. State symbol is aqueous. Strontium. Strontium's SR, What group is that in on the periodic table? Oh, no periodic table. Group 2, 2 plus ion. So Sr 2 plus, and we've used nitrate recently, so hopefully you remember that, NO3 minus. So putting these together, Sr NO3 2, aqueous. So we're going to swap partners. That's all that can happen. So I'm going to write the possible combinations over here. K plus and nitrate, Sr plus, Sr 2 plus, and sulfate. The order in which you write them, whether you write the potassium and nitrate first, or if you write the strontium and sulfate first, that doesn't matter. Because 2 plus 3 equals 5, and 3 plus 2 equals 5. We're adding things here, and so the order doesn't matter. We do want to have the positive ion and then the negative ion in the pair. It's Mr. and Mrs. Joe Smith, right? Why? Because we decided that's how we're going to do it. It's always the cation and then the anion. So let's check the solubility on these guys. Potassium and nitrate, we look that up, we find out that's aqueous. Strontium and sulfate, we find that sulfate compounds are generally soluble except, and strontium is one of the exceptions, strontium sulfate is insoluble. So then we've got KNO3 aqueous, and we've got strontium sulfate that is a solid. So we've got our products, and we've got our reactants, and then we balance the equation. On the left, 2 potassiums. Over here, there's only 1. So we need to put a 2 there. That multiplies everything after it. So now we've got 2 Ks on each side. Here's SO4, and here is SO4, 1 of each, so that's okay. Sr and Sr. How many nitrate ions? 2. How many nitrate ions over here? 2. So it's balanced. Any questions?